time for this nation to take a clearly leading role in space achievement, which in many ways may hold the key to our future on Earth.
It's one small step for man, one giant leap for mankind.
Today is a day for mourning and remembering. Nancy and I are pained to the core by the tragedy of the Shuttle Challenger.
The following program may contain coarse language, adult themes, and bad attempts at humor. Listener discretion is advised.
What is President Trump's goal? What is his vision? He wants to put an American flag on Mars.
Houston, Tranquility Base here. The Eagle has landed.
I am JEFF, also known as A Cosmic Bard over on Twitter/X, and this is the Lost Wanderer podcast for November 30th, 2025, coming to you from the new and improved ACS Serenade Observatory, orbiting high above the right and night side of the Earth. Tonight's top story, well, let's face it, sometimes the story of the week doesn't begin in the stars. It begins on the ground. On a quiet morning at Baikonur, where a Soyuz rocket was just simply sitting there waiting for the kind of routine preparations that have fed the ISS for more than 2 decades. Routine! Until a piece of ground hardware the size of a small house decided it had reached the end of its patience. A 20-ton swing arm, one of the massive steel structures that cradle a Soyuz before launch, fueling lines, data umbilicals, and the whole kind of nervous system of the pad jammed during a positioning sequence. And when it jammed, it twisted. Metal groaned, bolt sheared, and something ancient in the design finally let loose. I'm just going to double check something here. Perfect. There were no flames, no explosions, just a brutal mechanical failure. The kind that instantly kind of brings a halt to everything. Now, Roscosmos engineers rushed toward a pad suddenly full of questions. Was anything electrical compromised? Did the fuel lines take a hit? How much load did the support spine absorb? Can you even trust a structure after it absorbs that kind of shock? The answers didn't come quickly because, let's face it, they never do. And somewhere above, the ISS drifted across another sunrise, unaware that one of its most reliable launch channels had just snapped a 20-ton reminder of its own fragility. Because the ISS doesn't survive on magic. It survives on timing, on dockings and departures, on resupply rhythms so constant, we forget they're actually fragile. Soyuz vehicles carry humans and, I think, probably more importantly, cargo. They backfill missions when other nations fall behind. They are the quiet workhorses of low Earth orbit. But those workhorses depend on the old steel at Baikonur, and one of those steel arms just tore itself out of alignment. That's the part that makes spaceflight, maybe feel suddenly human again. Not dramatic failure, but the quiet kind, the kind that comes from age. When you wake up in the morning and just looked at the light wrong, machinery built from a bygone era. Now, Roscosmos says the damage is repairable, and it probably is. But inspections take time, and time is the currency the station is always short on. If this pad stays closed longer than expected, schedules will slip. Crew rotations will have to stretch. Supply chains will tighten. Orbital choreography gets a little more improvisational. Down here, it feels like it's an engineering problem. Up there, it feels like a soft shutter running through a ship that's older than most of the people listening to this broadcast, or at least close to it. The ISS has survived solar array tears, coolant leaks, unexpected thrusting firings, and more micrometeor strikes than anyone is comfortable to admit in public. It will survive this too. But each failure on the ground is a reminder the station lives on trust and timing, and that neither are guaranteed. Look at the photos from inside the cupola this week. They're sliding beneath, blue and bright. Inside, the crew moves calmly, checking the systems, sending down telemetry, heating meals, preparing for sleep. Life continues at 17,000 miles an hour, even when the world below hesitates. Now, there's a strange elegance of this moment. A 20-ton arm breaks on a remote pad in Kazakhstan, and somewhere in orbit, a tiny habitat keeps circling, waiting for the world to catch up. Like I said, the pad will be repaired. Schedules will have to shift, and the station will continue to turn another dawn after dawn after dawn. But you have to admit the sky feels a little more fragile, and the silence around Bacanor carries a weight only orbit may truly understand. And while Russia grappled with damage on the ground, another reminder of spaceflight's fragility arrived from orbit itself.
And now, assholes in space!
China is asshole! China is asshole! China is asshole! China is asshole!
Oh, yeah, my system's still slow after the reboot. I apologize for that. But up aboard Tianyang, 3 astronauts were settling into the rhythm of their mission. Experiments, daily maintenance, the quiet choreography of life in microgravity. When the alert came in, the return capsule, the vehicle meant to carry them safely back through heat and gravity and sky, had just taken a hit. A small strike, probably a shard of someone else's abandoned satellite, or more likely their own, or a fleck of a rocket body insulation drifting through low Earth orbit and nowhere better to be. All too often, we think tiny things don't matter, but in space, tiny things travel at 7 kilometers per second. A grain of metal becomes a bullet, a fragment becomes a threat, and a perfectly good spacecraft becomes a question mark. Now, China's flight controllers didn't hesitate. They did something rare, something that doesn't happen unless the math leaves no room for improvisation. They actually launched a replacement, a brand new return capsule, an emergency lifeboat thrown upward through blue and into the black, racing to rendezvous with the station like a rescue skiff cutting across the dark ocean. Now, it's not dramatic in the way, movies would imagine it. There's no heroism. There's no last second tick, 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 dock clamp snapping shut. It's quieter than that. It's a measured ascent. It's a cold orbital ballet. A new capsule taking position so 3 people don't have to wonder if their scorch mark on their original ride hides something deeper, something structural, something, well, that would probably betray them during re-entry. But this moment, this week, it carried a sharper undertone. Because experts across the world looked at that incident and didn't just say, oh, good call. They admitted this is the future and we're not ready. Look, we have rescue services for oceans, for mountains, for forests, for hurricanes. We'll pluck a stranded hiker off a cliff with a helicopter and think nothing of it. But if a crewed spacecraft gets hit by debris in orbit, the world's first reaction is, anyone, can you spare a rocket? Anyway, hey, you over there, do you have a spacecraft available? Guys, who can reach them? And at this point, there doesn't seem to be a unified answer. No international protocol, no dedicated space rescue fleet. Just a hope that one nation has a vehicle fueled, prepped, and pointed in the right direction. Well, this week proved the margin is thinner than has been advertised. It was a glancing strike, a damaged capsule, a replacement launched in a hurry. 3 astronauts now relying on a fresh machine because the old one absorbed just enough violence to make engineers worried. And that worry, quiet, professional, and probably mostly invisible, is what moves policy years from now towards something like a real rescue capability. For now, though, the crew aboard Tianyang is safe. Their new return capsule sits docked, pristine, pressurized, waiting for the long fall back to Earth when their mission eventually ends. But the lesson lingers around them like a bit of an echo. We have filled low Earth orbit with ambition. We've also filled it with debris. With progress comes leftovers. With dreams remains the shards of dreams. And every once in a while, the two collide. This time, thankfully, no one was hurt. This time, the solution seemed pretty straightforward. But in the soft hum of Tianyang's life support fans and the cold glow of the windowed horizon, the truth feels unmistakably clear. We are explorers. And explorers often need lifeboats, and not metaphorical ones, real ones, waiting, ready for the day when just a small strike ends up being something way more. And it was weird because as we think about this, for a few strange weeks, we had the skies over America's launch pad feeling a little quieter than they perhaps should have been. Not silent, SpaceX still flew at night, satellites still hummed overhead, but we had daytime launches being frozen in place, suspended under a rule that wasn't about rockets or debris or any of that. It was about people. When the U.S. government shutdown hit, the FAA's Office of Commercial Space Transportation lost its ability to oversee daytime operations. That oversight is mandatory on any launch that might intersect airspace, ground safety corridors, or hazard zones. Night launches could continue. Their flight paths were predetermined and easier to isolate, but anything scheduled under daylight needed FAA personnel on station. And FAA personnel, well, they weren't allowed to work. Rockets, it turns out, care deeply on timing. They care about windows, weather, trajectory, and the intricacies of celestial mechanics. They do not give a rat's ass about government funding bills. So for nearly a month, companies across the country held their breath as schedules slipped, vehicles rolled, paused, and teams stared at rockets that were ready, but now all of a sudden forbidden to fly. When the shutdown finally ended, the FAA returned to its consoles and almost immediately lifted the daytime ban, thankfully. It was like someone unleashed a pressure valve over the entire industry. And within hours, launch complexes along both coasts started to rearrange their calendars. Teams were reactivating flight simulations, safety reviews, and very importantly, range coordination. Payload specialists confirmed that perishable or time-sensitive cargo was still within mission tolerances, and suddenly the year's final push toward orbit was put back on track. Now, that said, the first flights to benefit weren't glamorous. It was a handful of commercial satellites, a weather monitor, a cluster of CubeSats built by university teams who had been biting their nails through the shutdown. But each one represented weeks of delay evaporating overnight. The broader industry, though, felt the shift even more acutely. Companies like SpaceX, ULA, and Rocket Lab maintained tight cadences. Missing one window, especially for SpaceX, can ripple into the next 6 missions. NASA depends on commercial partners for resupplies. Space Force depends on them for national security launches, and small companies depend on them just for the mere simple survival of meeting contractual milestones. A single bureaucratic freeze can shake all of this. And that's the part that they felt as the ban lift. The sense of modern spaceflight isn't just boosters and payload fairings, it's infrastructure, it's logistics, it's coordination. It's a global relay race where one missed handoff and you lose the sprint. And yet, when the FAA did return, the machinery of launch cadence spun back into motion almost instantaneously. It's amazing what private companies can do. The rockets didn't care what caused the delay. They just stood patiently waiting, as they tend to do. Like they do, waiting for the moment when the weather clears, when the range opens, and that human voice in the headset says the words they've been listening for. Proceed to terminal count. And then that way, in what mix of routine and wonder, another piece of sky became accessible again. Thankfully, not with fireworks or maybe even spectacle, but with a signature, a lifted restriction, and the unmistakable hum of a nation getting back to work. But while the FAA's return reopened America's sky, another corner of the launch world got a gentle little reminder that progress doesn't always rise. Sometimes it buckles. Down at the test stands in Boca Chica, the air carries a bit of metallic hush. A kind that settles just before a machine shows you, just what it's really made of. SpaceX rolled out its new version 3 Super Heavy booster, the largest first stage they've ever attempted. A towering cylinder of stainless steel meant to lift Starship toward lunar and further ambitions. This test, well, it was relatively straightforward. Got pressure loading, the mechanical honesty check every rocket endures. You fill the tanks, you push the limits, and you give a gentle listen to the metal as it creaks and groans. This time, though, the metal decided to answer in return with a bow. A sudden deformation rippled down one of the booster's rings. Not a rupture. No, not a fireball. No. But a visible buckle. A structural fold that told engineers unequivocally that this iteration had reached its tolerance. It's that kind of failure that actually feels a little more intimate than dramatic. There was no explosive shockwave, no shattered hardware scattering across the pad. Just a massive test article quietly slumping against itself like two elephants tied Siamese to the nose and go. Some of the olds in the audience will get that humor and appreciate it. A reminder that the physics of ascent begins with the physics of endurance. SpaceX has walked this road many, many times. Starship's early prototypes split, crumpled, tore open like soda cans under pressure. Each failure became a new blueprint. Each blueprint became, the next iteration. Progress in their world is an unbroken chain of, maybe not yet, but soon. Oh, yes, soon. And let's face it, version 3 has raised the stakes. This booster is part of the architecture that NASA is eventually counting on for the moon, heavy cargo, lunar infrastructure, and cadence of Artemis itself. So when it bends, the ripples don't stop at Boca Chica. They touch timelines, they touch budgets, and of course, they touch expectations that were already stretched to the thinnest. And within minutes of the buckle, teams were analyzing stress patterns, adjusting reinforcement concepts, and reviewing weld sequences. There's no drama inside those control rooms, just a rhythm of engineers now doing what they've always done. Try to learn quickly, fix decisively, but most importantly, move forward. And the truth is, this kind of failure is not even really a setback. It's tuition you pay for building the biggest rocket in human history. Soon, another booster will take the stand, probably a little stiffer, probably a little stronger, carrying the lessons written in today's crumpled ring. That's the arc of rocketry. The sky just doesn't grant progress. It challenges you to earn it over and over and over again. But under the Texas sun, besides a booster built to touch the moon, you can almost hear a future exhale, a long, patient breath that says, Try again. You're so close. And while Starship learned another hard lesson on its test stand, NASA confirmed something many teams had already suspected and some had even announced. Artemis 3 is shifting to 2028. Now, I know the moon isn't any further away. The engineering simply needs more time, which only gives credence to those people who don't believe we've ever been to the moon more legitimacy. But NASA's announcement doesn't come with drama. It just comes with simple number schedules, milestones, and that unrelenting math of a program where every piece depends on every other piece. Artemis 3 isn't a single rocket or even spacecraft. It's a chain of systems that all have to work on the same day in the same order and without any real hesitation. And right now, that chain is not ready. Yeah, you could say Orion is flying okay. The Space Launch System is progressing. Kennedy's ground systems are, for all intents and purposes, are in place. But the lander, the Starship-based human landing system, still has a few major checkpoints ahead of it. It needs long-duration flights. It needs propellant transfer tests. It needs a demonstration mission that shows SpaceX can move tens of tons of cryogenic fuel between vehicles while everything is coasting along through microgravity. All of this takes time, and none of it can be skipped. Now, the booster buckle didn't cause this delay, but let's face it, it didn't help it either. It reminded everyone involved that scaling Starship in the lunar lander isn't about speculation, it's about reliability. Artemis 3 can't launch until NASA has confidence in the full stock from the ground to the lunar surface, and most importantly, back again. So the timeline now slides to 2028. It's not canceled, it's not abandoned, just shifted the way complex engineering often is when risk margin needs to widen a bit. And inside the program, the mood is still steady. Engineers are just simply adjusting their milestones, and astronauts may have to change their training cycles. The flight controllers will, of course, revise timelines and mission sims. There's a bit of disappointment, but in the end, it is work. And the goal remains the same, a crewed landing near the moon's southern pole, where ice waits in shadowed craters and the future lunar exploration begins. And though Artemis has maybe stepped back a little on the calendar, there is another player who used a moment to step forward quietly, but with an unmistakable ambition. And I'm not even going to make fun of him this time. Blue Origin confirmed that it's developing a super heavy variant of its New Glenn rocket, a larger, more powerful evolution of the booster that has yet to fly its first orbital mission, but this upgraded version isn't a small tweak. The deliberate push in the same performance class as Falcon Heavy and possibly eventually Starship. And with their last launch, Blue Origin looks like it might be, I'm not going to say catching up because right now SpaceX's record is simply, pardon the pun, otherworldly. But Blue Origin looks like it's at least going to enter the same arena. Now, the company hasn't really released every technical detail yet, but early outlines point to a more stretched first stage, expanded propellant capacity, and a higher thrust BE-4 engines to match the new increased mass. And its goal is relatively simple. They want to lift heavier payloads to higher orbits with enough margin to support possible lunar infrastructure, deep space cargo, or large-scale satellite deployments. In other words, they're building a rocket for the next decade, not the last. Now, New Glenn, it already stands tall at 98 meters, with a reusable first stage designed to land on an ocean platform just like Falcon 9 and like it showed it can actually do. The super heavy configuration would push those capabilities a little further. What makes this announcement interesting isn't just the hardware. As much as the hardware is amazing, and if you watch the launch, you saw the rocket basically come down looking brand new, clean because of the different fuel type they used. It looked beautiful. I hate saying it because Amazon and Jeff Bezos fucked up Rings of Powers, but the rocket itself looked absolutely stunning and amazing. But the timing. SpaceX has, let's face it, dominated the heavy lift conversation for years. ULA has Vulcan coming online. The Chinese Long March fleet continues to scale upward. And now Blue Origin is signaling that maybe New Glenn, just maybe, will not be a single static vehicle, but a family, a platform that can grow with ambition rather than being outpaced by it. And the company, to its credit, has also emphasized cadence, not just one launch, but many. Not just capability, but reliability. Bezos himself put it bluntly in a recent interview. Blue Origin intends to, quote, move heaven and earth, unquote, to support NASA's path back to the moon for the first time, for those in the audience that are like that. There is a sense of quiet confidence in that. It's not theatrical. It's not even boastful. Just a steady push forward from a company that knows it has some catching up to do and is taking its first steps to doing so. It'll be amazing to see. And the sky will get a little more crowded, but maybe our dreams will become crowded as well. With that, let's take a little break of about 3.5 minutes. We will be right back. Welcome back. Hope you enjoyed that little intermission music for tonight. And as the second half begins, our attention turns to something universal in space flight. How crews actually eat when home is hundreds of miles below them. Now, I do apologize for this first story, but it has to be talked about. In Europe, the ESA has begun testing a new food production method designed for deep space missions and long duration habitats. It uses a microbial process called power to protein. Yay, protein, where microbes convert carbon dioxide, nitrogen, hydrogen, and minerals, including nutrients recovered from astronauts' urine, into edible biomass. Now, it sounds a bit like science fiction workaround, but it does solve an actual real problem. Carrying food for months or years becomes unrealistic beyond low Earth orbit. A closed-loop system that turns waste and atmospheric gases into protein would reduce the resupply needs and allow lunar or maybe even Martian crews to produce food on site. As you're not going to be surprised with, the early samples are not gourmet. They resemble a protein-rich paste or powder, similar to nutritional supplements with a mild flavor and no texture beyond what any process adds later. But the system works. And if we're being honest, in spaceflight, works is the requirement that matters. And meanwhile, over on the China's Tianyang space station, astronauts tested a completely different approach to food preparation, a compact space oven designed for grilling. Instead of relying solely on prepackaged meal, this oven uses controlled conduction heating and airflow management to warm food safely in microgravity without creating smoke or free-floating particles. In their demonstration video, the crew heated meat sealed in foil pouches, then opened them carefully to prevent drifting crumbs or droplets. Now, it wasn't grilling in the traditional sense. There were no flames, there was no char, but it produced freshly heated food with noticeably improved texture and aroma compared to standard space meals. The technology is simple, but it is important. Adding even small variations in meal preparations can improve crew morale, appetite, and long-term nutritional health, critical factors for missions lasting months at a time. So in a way, we had two different developments, opposite ends, basically of the same challenge. ESA pushing towards sustainable long-duration protein production, and China improving meal quality aboard a current generation station. And somewhere is a South Korean camper going, "Can I get that grill?" But after spending a moment on the delicious thought of future of food in orbit, we have to shift to a rare story about saving something already out there. A spacecraft that was left drifting, and the company bold enough to bring it back, or at least try. The Swift Observatory, launched in 2004, was never supposed to live this long. It was built to study gamma ray bursts, the universe's brightest, briefest flashes, and over the years it evolved into the quiet workhorse of high-energy astronomy. But aging satellites, they don't really get retirement plans. Their orbits decay, their components wear out, and eventually the mass says, it's time to say goodbye, like Leonardo DiCaprio says to his 25-year-old girlfriend turning 26. But Catalyst Space Technologies wanted to disagree on the first part, not the Leo part. They're basically a relatively small company compared to the giants of the launch world, but earlier this month they announced something almost unheard of. A plan to rendezvous with Swift using a modified Pegasus-class launch vehicle and attempt a stabilization mission. Not a full repair, not a refit, but an effort to extend life. Add attitude control, push the orbit upward, and buy scientists a few more years of data from a telescope that actually still has value. The mission profile is a bit unusual. Pegasus launches from a carrier aircraft, not a pad, meaning the rescue vehicle can be deployed from virtually anywhere with clear skies. Catalyst plan uses flexibility to match Swift's declining orbit with minimal fuel expense, a kind of orbital intercept that leans less on raw power and more on math and clever trajectory design. Now, once the spacecraft reaches Swift, the goal is to dock with the satellite's bus structure using a set of articulated capture arms. If they succeed, the attached module would provide fresh avionics, small electric thrusters, and a control package to maintain orientation and counter drag, unlike elementary school libraries. Oh, did I say that out loud? But if they fail, there's no debris net, no second attempt waiting in the wings, just an aging spacecraft that will continue its slow fall toward reentry. Now, NASA isn't leading this operation. They've acknowledged it. They've even supported some data exchange, but the initiative and the financial risk all belong to Catalyst. And to me, that's what makes this mission interesting. 20 years ago, a rescue like this would have been the domain of national space agencies. Today, it comes from a private company with a modest budget and an ambitious engineering team working to prove that orbital servicing doesn't have to be science fiction or even to the exclusion to multi-billion-dollar defense contracts. If they pull it off, Swift won't just survive longer, it will become proof that old satellites do not have to die quietly, and we don't have to send up Clint Eastwood to save them. They can be helped, stabilized, and given one more chapter and a proper ending. And in a sky filling with aging hardware, this idea actually might matter more than I think some would admit. But another aging spacecraft made headlines for helping itself this week, quietly proving that autonomy in orbit is no longer a concept, but now could be considered a capability. Earlier this month, an Earth observation satellite operated by Joint European Commercial Team experienced a guidance anomaly. Nothing catastrophic. No tumble, no loss of contact, but enough of a deviation to trigger the onboard fault detection protocols. Normally, this is the moment when ground controllers would step in, issue commands, and guide the spacecraft back into attitude lock. This time, the ground didn't get there first. The satellite's onboard AI control system detected the error, classified the type of rotational drift, and initiated a corrective sequence automatically. Using its reaction wheels and star trackers, the system calculated a recovery path, counter-torqued the drift, reacquired the target attitude vector, and resumed its imaging schedule, all before the next contact window. From anomaly to recovery took mere minutes, not hours, not a ground team scrambling, minutes. Now, granted, the speed isn't what makes this important. It was the demonstration of independence. In low Earth orbit, satellites circling the planet roughly every 90 minutes, spending much of that time out of direct communication range. When something goes wrong during those blind arcs, recovery usually has to wait until the next ground pass. That delay can cost data, fuel, and, well, in some cases, the aircraft or spacecraft itself. An autonomous system that can diagnose and correct drift in real time is a change in the equation. It means fewer missed imaging cycles. It means less wasted propellant. It means spacecraft can survive anomalies that used to become mission enders. Now, the AI didn't override mission control or rewrite its operating limits. It followed the constraints embedded by engineers, but it did demonstrate that what industry has been predicting for years, the era of satellites that can maintain themselves, is upon us. Now, this same technology is being explored for deep space probes, where communication delays stretch from minutes to hours. I know, Wardy, this is how you get V'ger. I know. But a spacecraft at Mars or the outer planets can't wait for Earth to troubleshoot every hiccup. If this low orbit test is any indication, autonomy will soon be essential for missions beyond the moon. Now, engineers reviewing the event confirmed that the system responded exactly as designed, identified the drift mode, prioritized safety, executed controlled recovery, and logged the entire sequence for later analysis. There was no drama, no panic, just a machine proving that spacecraft can take care of itself if and when they need to. Now, I find it interesting because you have some satellites that may not be making groundbreaking news or in the scene a lot. Some seem to be very quiet, and some are doing it so quietly, mapping things like, oh, I don't know, the universe with a precision no human hand could ever match. And one such thing is the Euclid Space Telescope, launched by the European Space Agency. It has completed its first year of full scale observations. And those numbers that are coming back, they're a little bit staggering. Now, in just 12 months, Euclid has cataloged 1.2 million galaxies, each one a collection of hundreds of billions of stars, all captured across the patchwork of imagery and spectroscopy deeper than any wide field survey attempted before, which is why I am working on the Stoner equation to replace the Drake equation. Now, Euclid's mission is simple to describe and incredibly difficult to execute, though. Map the large-scale structure of the universe and help astronomers better understand things such as dark matter, dark energy, the two invisible components that seem to shape cosmic evolution. To do that, Euclid carries a 1.2-meter telescope, a high-resolution visible imager, and a near-infrared spectrometer. Together, they're building a three-dimensional map of the sky, measuring how the galaxies actually end up clustering, how light stretches across the distance, and how cosmic expansion changes with them. The telescope's wide field of view is one of its biggest strengths, where instruments like Hubble tend to zoom in to tiny patches of sky for ultra deep detail. Euclid is scanning with broad swaths, spotting galaxy groups, filaments, voids, and giant arcs of structure that reveal how gravity has sculpted matter over billions and billions of years. That said, among the early findings, we have massive galactic filaments stretching hundreds of millions of light years, precision weak lensing measurements showing how dark matter distorts background light, new dwarf galaxies previously hidden by low surface brightness, improved distance estimates for clusters in the cosmic web, and the beginnings of a data set that will ultimately map billions of galaxies over the next 6 years. I know sometimes we think of the image as a photo. We should think of it in a bigger, grander scale. It's a data cube. We have color, position, redshift, brightness, structural information that together reveal the shape and the motion of the universe itself. And what matters and what makes this so important is the scale of it all. Dark energy, the force accelerating cosmic expansion, leaves faint fingerprints in how galaxies drift apart. Dark matter leaves equally faint signatures in the distortions of the background light. The more galaxies you measure, the clearer those signatures will become. Now, Euclid's first year release isn't a conclusion. It's just a good foundation to build upon. A massive, precise, carefully calibrated starting point that will let cosmologists test ideas about the universe's fate with far more accuracy than they've had before. Now, I know I talked about this a little bit on my guest appearance on Juxtaposition. Once again, Orty, thank you for letting me fill in. Got to talk about it here, too, on this program. The Interstellar Visitor 31 or 30I Atlas. Only the third confirmed object to arrive here from another star system has now passed perihelion, giving astronomers a rare window to capture a detailed image while it was brightest. This new deep exposure shot reveals exactly what physicists predicted: a break nucleus, a well-formed coma, and a dust tail shedding material in a smooth arc behind it. None of this stopped Harvard's most headline-friendly theorist, Avi Loeb, from briefly and continually suggesting the object's shape might hint at something engineered. But Atlas itself wasted no time providing the rebuttal. As it heated near the sun, its outer layers began fragmenting, irregular chunks breaking off, volatile ices venting into space, and the classical behavior of a natural comet under thermal stress. If this were a spacecraft, it would be one that arrived rusted, shedding panels and leaking gas. And I know, Firefly makes it possible, but it's not exactly the galactic equivalent most would think of a diplomatic first impression. That said, spectroscopic analysis backed it all up. Observatories detected carbon-rich dust, silicates, cyanide compounds, and diatomic carbon, the entire chemical structure set found in comets, but none of the material associated with anything that we would deem artificial. Its brightness curve, rotation, and structural shedding all match standard comet models with way too remarkable accuracy. That said, even it now seems its trajectory is stubbornly natural. I know people that change course. It is really following a clean, hyperbolic escape path with no real thrust, no anomalies, no deviations, just a smooth slide of an interstellar object passing through a gravity well and continuing on because the bugs missed us. Now, unlike Umamau, which sparked years of, debate fueled by weird geometry and very sparse data, Atlas actually ended up being very cooperative in the end. It behaved like a comet, it broke up like a comet, it outgassed like a comet, it photographed like a comet. In chemistry, it screamed, "I'm a comet," which leaves very little room for, my people or other extraterrestrial engineering, unless the aliens are building their starships out of frozen methanol, ammonia, and dust grains. And trust me, that doesn't work because they wouldn't be staying airborne long. But as it recedes into the dark, Atlas gives astronomers a clearer picture of what interstellar debris may actually look like. Not mysterious and not even exotic to the large scale, just a fragment from another stellar nursery passing through, lighting up briefly, and moving on. But the fact that we're being able to catch this and see it, eventually, that means Avi Loeb will be correct with one of these. I'm not sure if I'm going to enjoy that day or hate that day. I'll leave that up for you to decide for yourselves. But after watching an interstellar comet drift back into the dark, we got to face it. It's not hard to look further, far beyond debris, planets, and even galaxies, toward the question that waits at the edge of all cosmology. How does the universe itself end? I've done a ITC on this very matter back in the early days when I only did 30-minute recorded shows. So we've gotten even more data since then, but it's still the answer itself is not a singular answer. There are still several competing models, each grounded in physics, each depending on how dark energy behaves, how matter thins out, and what happens to the fundamental particles that make up everything we've ever seen. Now, of course, the most widely accepted scenario is the heat death, or also known by its other name, Big Freeze. I always thought that's what my ex-wife was called, but anyway, in this model, the universe keeps expanding forever, galaxies drift apart, stars burn out, black holes evaporate through Hawking's radiation, the cosmos then becomes a thin, cold field of stray particles and fading photons stretched across distances so large that no structure remains. There's no collapse, no explosion, just a long, slow slide in the thermal equilibrium where no energy differences exist and therefore nothing can happen at all. Also, like the marriage second one that I had. Now, another possibility is, of course, the Big Rip. This also depends on a version of dark energy that grows stronger over time. If it increases faster than matter can resist, the expansion of space eventually overwhelms everything. Galaxies will tear apart, stars will disassemble, planets will disintegrate, and even atoms will lose cohesion. The timeline varies by the model, but the mechanism is the same, expansion accelerating until structure becomes impossible. But there's also the big crunch. once considered the leading idea before dark energy was discovered. In this version, the universe eventually just stops expanding. It reverses direction and collapses inward. Galaxies converge, background radiation heats, and everything falls back into a dense, hot state similar to the Big Bang's origin. The universe creation, not the show that was on CBS. Current data strongly suggests this won't happen, but it remains mathematically valid if dark energy behaves differently than we expect. And hey, we barely know what dark energy is, so it could very well do this. In a related idea, the Big Bounce argues the collapse doesn't end everything. Instead, the universe rebounds into a new, wonderful, glorious expansion, creating cycles of birth and death stretching across unimaginable time, which leads to some people think that's why we have deja vu. It's speculative, yes, but not impossible. On the smallest scales, particle physics offers another long-term process. Proton decay. If protons eventually break down something not yet observed, then matter itself has an expiration date. Even in stable thermal universe, that decay would slowly erase stars, planets, and every atom. None of these endings are thankfully soon. Even the most dramatic models operate on scales of tens of billions to quadrillions of years, far beyond the lifespan of stars, galaxies, or, well, let's face it, probably anything humans will ever touch. So cosmology isn't predicting tomorrow. It's mapping possibilities on a canvas larger than time itself that we understand it as. And after talking about the end of the universe, I figured we could end the show with something a little lighter. Something that doesn't, involve proton decay, evaporating black holes, or the long, slow cooling of everything that ever was. How my last marriage could get any cooler, I don't know. But hey, here we are. And we have, of all people, Amazon to thank for this. I know what you're saying. Wait, Amazon? The people that brought you Rings of Power? Yeah, I'm talking about them. Please, please don't ruin this one, Amazon. Please. Because, yes, it is finally official. They've greenlit a brand new Stargate series. No casting yet, no trailers, no set photos, just confirmation that a writer's room is assembling and the project really is moving forward. And buried underneath all the corporate press language is the promise or the hope that they're aiming for a return to the classic tone, exploration, adventure, ancient mysteries, and at least one moment per episode where someone insists the wormhole is totally stable seconds before it sparks like a cut power line. And after the stretch of space news we've covered tonight, pad failures, buckling boosters, emergency orbit to ground lifeboats, the idea of a show where the biggest problem is, oops, we dialed the wrong planet again, actually sounds a little relaxing as long as General Carter is leading Stargate. Now with that, I think it's time to turn to the sky. For the next 2 weeks, the night settles into its early winter rhythm, crisp, steady, and full of familiar winter landmarks. Shortly after sunset, look low in the southwest for Venus. It's sinking fast toward its next solar conjunction, so visibility will drop as the December continues. This is one of the last easy windows to spot it before it disappears into the sun's glare. To the east, Jupiter dominates the evening sky. Even a simple pair of binoculars will reveal its 4 big moons shifting position night by night. A small, reliable, glorious show as winter sets in. And just above Jupiter, the Pleiades reach higher each evening. Even under modest light pollution, the cluster's cold blue sparkle is very unmistakable. And closer to midnight, Orion climbs into full view. His belt clears the horizon around 11, with the Orion Nebula glowing faintly below, a soft smear of light worth taking in if the air is clear and Mother Nature is not snowing on you. Meteor watchers should mark December 13th and 14th for the Gemini meteor shower. This year, the moon will be in a waning crescent, meaning darker skies and good conditions. Under clear weather, emphasis on clear, The Geminids can easily produce several dozen bright meteors per hour. Now to the full moon. December brings the cold moon, reaching full illumination on December 4th. In several native nation traditions, including Northeast nations, the moon carries names tied to winter's arrival and the long nights ahead. One Abenaki name is Pebunkas, pronounced probably wrong, and I apologize in advance for whatever I just did to that pronunciation. Please, Abenaki, do not scalp me. Send emails to the alien at klrnradio.com, because right now our servers are down, so it won't be sent. Anyway, this full moon rises at sunset and climbs high through the evening, bright enough to cast long shadows across frost or snow. Finally, in the pre-dawn hours, look southeast for Saturn, riding low and steady. It's faint but unmistakable when the horizon clears. So that's up your sky for the next 2 weeks. Bundle up, look up, maybe toss Mother Nature a middle finger if it's snowing too much and you can't see any of this. And as always, please keep wondering. So that's it for tonight's transmission. Thank you for tuning in whenever and however and why ever you do. Special thanks to NASA, SpaceX, Space.com, Ars Technica, NASA Spaceflight, Popular Mechanics, and everyone out there keeping humanity's eyes on the stars. With me at the helm, the executive producer plotting our next course, and the ship's computer in the back whispering star maps through the static. This has been the Lost Wanderer podcast. Until next orbit, I hope you enjoyed the show, learned a little something, maybe had a laugh or two as well.
The universe is a pretty big place. It's bigger than anything anyone has ever dreamed of before. So if it's just us, seems like an awful waste of space. Right?
When I was young, it seemed that life was so